Okay, everybody. Topic of the day is symmetric key ciphers. What I'm going to do, this is going to only take about a half an hour. I've been through the slides that Dave created. It's really gnarly, and most of it you don't actually have to know, frankly. Um, I mean, it's good to have gone through it, good to have touched it, but um, it's pretty grunge. Okay, it's pretty low level grunge going down. So the other thing too, I want to just say about this, symmetric key ciphers is a bigger topic than just DES, but that's what we're talking about is DES. This entire lecture is simply DES. Okay, and so be that as it may, we're going to dive deep, and at least you will have seen the low-level grunge of DES. And we talked broadly the last time about ciphers. Here's the basic punchline. This might not even take a half an hour, but here's the basic punchline. You do two steps. The first is kind of the key manipulation step, and then the second part is the data manipulation. Okay, the data encryption step. The first step is basically, and this most of the slides are confusing, just saying, and so we're going to try to walk through it. But what we do is we take a 64-bit key, which is our encryption key, and we build from that 16 separate 48-bit keys that we build from that initial 64-bit key. We'll show you how to do that. When you're done, now each key is derived from the key before it, but we keep all 16. Okay, we hang on to them. Then we take a 64-bit block of data, chunk of data, and we encrypt that 64-bit block of data using the first of those 16 keys. Then we take that value and we encrypt it with the second key. Then we take that value and we encrypt that. So we literally encrypt it 16 times. The same thing gets encrypted 16 times with 16 different keys that are all derived from the initial key that you provide as your key. One of the interesting dynamics is like why, right? I mean, if you know the recipe and you have the first key, why are you doing that many times? You know, taking this, creating an encryption, encrypt the encryption, encrypt the encrypted encryption, and do that 16 times. Why? And I think that the primary reason is remember that decrypting in a sort of faster, better than brute force kind of way requires that you're able to see certain kinds of patterns. Well, when you take something and you encrypt it and encrypt it and encrypt it and run it, it's like taking I don't know, pancake batter or something. And if you whip it and whip it and whip it, pretty soon there are like no lumps left. I mean, you just can't see any lingering patterns. If you fold it a little bit, you can still look at the powder and go, "Oh, pancake batter," or whatever. But if you keep folding it, folding it, folding it, not only do you ruin the pancake, but you lose the ability to see patterns, right, popping out. So that's it. And then to decrypt, you go back the other direction, starting with the same key, generating the same 16 keys, working it backwards. Okay, so that's all. That's all. That's what DES is, and we'll kind of walk through the rest of this. So here's what happens. The very first step is you take this is the original master key, the 64-bit key. Notice that it goes, ignore this deleted parity bits. When that was there, 1 through 8, and then there's, 8 rows and 8 columns, 64 bits. You delete the parity bits, and basically what you do is you look at, okay, see the little note I added? I added a few notes. Numbers equal the bit position. So that's bit position 1, 2, 3, 4, etc. So it's like 1 goes here, 2 goes there, 3 goes there. But what's actually happening is you start in the lower left hand, and for the first 4 rows, you go up. Look at the rows across here. Now go up 57, 49, 41, CM, 33, 25, 17, 9. You go up 7 bits. Then you keep going and you keep going up and then start over, up, and then start over at the bottom and go up. And you do that until you've filled 4 rows with 7 bits each. At which point you get down here to the 36, which is there. Then you pop over to the lower right-hand side, 63, and go up. There we go, 63, right, through 15. And then you go 7, 62, 54. And again, those numbers just represent which bit over here, as you do this matrix manipulation, which bit over here, becomes that bit over there. That's what that's all about. When you're done, you have a 56-bit master key. That's a permutation. You split that guy in half. Again, the details here, it melts your head just a little bit, but you view this as being 2 halves, C0 and D0, the left half and the right half. I can't even speak. The left half and the right half. And you hang on to these. Now, this recipe down here is where this all kind of fits together. What you do is this permutation allows you to obtain this half of K sub n, and that permutation, so basically C0 with that permutation applied gives you this half of K. The right half of this permutation of the master key, with applying this permutation, gives you the right half over here of K sub n. So the way to look at this is we've just applied the original master key. We now have C0 and we have D0. So that would be C0. So when 0 is n minus 1, then we're trying to now apply, and we know, so when when we got C0 and D0, we're going to try to create Cn, which would be 1, and Kn, which would be 1, okay? So K sub 1. So once I have C0 and D0, I can create the first 48-bit key, okay, for round 1. And so I take the 28-bit key, see that I've got this 56-bit master key, 2 halves of 28. I apply this permutation, okay? Then there's like special recipe tables for rotating the each row of C, rotating it left, and that's rotate means the bit that pops out comes back around. That gives us C1. And then I did this thing wrong. C0, that original right here, gets rotated. So 9 would go to the left, 57 would come around back on the right. And that would give us, and as you can see right here, it's trying to show you, it's not doing a good job of it. But basically, where's 2? Yeah, I don't know. To me, these numbers are not even helpful, okay? But because they're just not that intuitive. But anyway, you take C0, you rotate it, that gives you C1, you apply this permutation, and that gives you the left half of K1, okay? And then you do the same thing on the right-hand side with D0, rotate it, that gives you D1. It does kind of show you, I don't know, honestly, I think that these made some sense for a moment once in my head, and then they vanished out of my head. Anyway, that gives you K sub 1, okay? So that's a key. You save it away. You save that key away. Now you have C sub 1, you put C sub 1 up here. Rotate it and make C sub 2. Make D sub 1 and D sub 2. And now you get K sub 2, save it. So you're saving this, you do it 16 times. You save K sub 1 through K sub 16. Okay? That's the generating of the keys. So that's what you're doing. You take one pass through from that initial permutation from this original master key to the 56-bit master key. You do that permutation, and then you do 16 rounds of key generation. And every single round generates a new 56-bit key or 48-bit key, sorry, for generating 48-bit keys. And somewhere along the line, what I can tell you, and I don't remember the details, but you're actually dropping some of the keys. You get 28 bits, but you get double 24. So there's some keys that don't make it, or some bits that don't make it. Okay, I now have 16 keys. Now I can encrypt my data. So what I do here is I take a block of data, a 64-bit block of data. I view it as a matrix, as an 8x8 matrix of bits. What I do is I rotate it and interleave. So I take columns B, D, F, and H, right? B, D, F, and H. And then columns A, C, E, and G, A, C, E, and G. Rotate those and interleave them, and which basically is this permutation right here. That's the original bit pattern. That's the next bit pattern. Okay, so I permute the data block. Then I take that 64-bit input of data. All right, I split it in half to two 32-bit halves, the left and the right. Okay, the 32-bit right half, I save it over here to be the left half of the output. Meanwhile, I take that same value, I run it through a mangler function. It's just like, again, I'm trying to remove any patterns, any recognizable patterns. I take that, I run it through this mangler pattern in which I apply the key, okay? The 48-bit key for that round of DES. I then take the left side, the mangled right side, I XOR them together, and that gives me the right side. I now have the new left and the right. I now put that back up to the top. Now I'm round 2. Same thing. Split them. Right goes to the left. I mangle that half. So I mangle half of it with the key. And then the next time around, because I've switched them, I mangle that half. I switch them and I mangle. So I'm remangling, 8 different times. Each half gets mangled 8 times. And when I'm done with that, I have every round of it gives me an encrypted version. But by doing it 16 times, I'm just much, much more mangled. Here's the mangler function, which is, I'm not even going to get into it. I'm just going to say that I take 4-bit chunks of R, which is, the right side right there, 32 bits RN. I take 4-bit chunks of R. I grab the 4 bits and the bit on either side of it to make a 6-bit value. So I expand it into this 6-bit value. I take a chunk of the right and I take a chunk of the key for this round. I XOR them together to give me 6 bits. I then run it through this SBox function to get me 4 bits back. Yeah, we're not done yet. This is the SBox function. You see why? I mean, it's insane. This is the SBox function. The idea here is, here comes a 6-bit value coming in. The 6-bit value is a result of XORing a 6-bit chunk of the right half with the corresponding 6-bit chunk of the key for that round. And what I get is a 6-bit value. I take the 6-bit value, for example, 011100. I strip off, I take the middle 4 bits and I use that as my column index. And then I take the beginning and end bits and I use those as my row index. So row 0, column 1110 gives me 000. It's just a table lookup, and that is the S function, the SBOC function to give me these guys back. Okay? So that then pops out the mangular function. I XOR that with the left. So I've got the right being kind of, munged and XORed with the key, that value being XORed with the left, and all that does is create this 32-bit R. The miracle to me, and it's really all math at the end of the day, and I'm not a mathematician, I've had plenty of math, but I've never, not a mathematician, is the mathematics, the science, the whatever, what do you call it? The math behind all of that is just, to me, a little crazy, and it kind of feels emotionally, it feels like crank it, like, why is that the thing? Why was that the guess? Why was that the thing that they decided to do? Like, I don't know. I mean, I don't know down at that level. I know that it works, and I know that we can decrypt the exact same way, running it back through. Why, at a deep math level, I don't know. So that's our high level view again. I've got 16 rounds. So I start with 16 rounds of key generation. Then I do 16 rounds of data encryption of 64 bits each. Now that's a repeated slide. This is the last slide. I told you this is not even going to take a half an hour. I mean, no, practicing and getting good at it, knock yourself out, Also, to me, this is material at this depth. I don't know. I feel like it's too much, too deep for this class. Even the book, like, in the notes, it's kind of like the book doesn't go into this much. Well, there's probably a reason for that, and I'm maybe more in line with where the book's at than to go this deep. Oh, a question you might encounter, a horrible question you might encounter. Let me see. I'm going to munge this question a little bit when it's actually on the exam, but here's some things you should know. You got to know that you make 16 keys and then you do 16 rounds of encryption, okay? And that when you're in the encryption phase, this is the encryption phase where the mangler function lives. So the steps involved in executing DES encryption round N, so a given round, are listed below in the sequence that they occur. Okay? One of the steps listed is not a part of DES round N. Okay? Now just remember that DES round N refers to a round of encryption. It does not involve the generation of keys. That's the biggest thing you have to remember. The generation of keys happens during a key generation phase. First, 16 rounds of key generation. Then, and I don't like the fact that he's calling it, a round of DES, because DES is the whole thing, and it involves rounds of key generation and rounds of encryption. So I don't like that, and I'd probably change that to say DES encryption round N, because there are N rounds of key generation. So to me, that's a semantic, too much hinging on too small a semantic detail. The first question, which of these is not a part of encryption? Use the 32-bit output field from the mangler function to generate the 48-bit per round key for the next round. Well, you don't generate keys. And all the rest of the other options almost don't matter if you just remember that the encryption rounds are not generating encryption keys. They're generating encrypted values, which become the data. They're encrypted data. They use the keys that have already been generated They generate encrypted data so that you can turn around and take that data and use it as the input to the next round of encryption. Okay, that, believe it or not, I mean, that's it. And then this is, if it's helpful to you, use this as a refresher. I don't know how helpful, because to me it's too much detail. And for me, the picture, I mean, they're there in the slides. You know, let me just freeze on this for a second. 24-11. And anyway, there we have it. I would look at things I would look at and try to just understand. Understand this, that there are 16 rounds of key generation and an initial permutation, 16 rounds of key generation, and then a final permutation. This is the initial permutation right here. And then this is the key generation process. You don't have to know it down to the bit because we're not going to code it up. Having generated 16 keys, we now do 16 rounds of data encryption. And this is where you permute the data block and then grab each of the permuted data blocks and then run this bad boy 16 times, including the mangler function, which is this, in which the corresponding chunk of the key for that round is XORed with the chunk of permuted data for that round to create a 6-bit value, which is mapped to a 4-bit value. That's DES in a nutshell. And then that's just simply the S box lookup. Dun dun. Those are the highlights. And if I were to build the slides myself, which if I ever teach this class again, I certainly will. L'chaim. Those are the main things to keep in mind about it. And you just run the thing the other way to decrypt. And it's the same starting point, same symmetric key. So it's the same key that you share that's private. Okay, that's it. I'm going to jump on, that's 24. I am going to jump on 25 like a madman and see if I can get it done tonight. And I'm just going to keep going. There's only now 4 lectures left. And we are on, I mean, date-wise, we're done through Thanksgiving with material, and it's just sitting here on YouTube for you. And then I'm available on Discord if you want to jump on at all to ask me questions. And then we've got 4 more left, and the next one up is RSA. And that's all I got for today. Good luck. Hang in.